So we start today our class with a concept that will be accompanying us throughout the time, which is network theory. We will be explaining many concepts in logistics based on these 2-3 aspects that we will see today. Okay, and they are very important because they help us understand a lot of things also of real life. So network theory is a theory being developed to explain many physical nature, many physical and biological issues, also used in logistics, and can be applied in this case. As you will see, these concepts are very useful. So imagine we have this network. What is a network? Intuitively, you have nodes and you have edges. Edges are the things connecting the nodes. Okay? These nodes could be people, these nodes could be factories, these nodes could be machines, these nodes could be Facebook users, anything. Okay? So you can describe a lot of phenomena with network theory. This is why what you're learning today is very important for your future. We describe networks mathematically with graphs. So a graph is a set of nodes, a list of nodes, 1, 2, 3, 4, 5, 6, 7, 8, and a list of edges. I connect 1 to 4, 1 to 2, 1 to 5, 2 to 5, and so on and so forth. Okay, so it's a list and a list. In this case, we have n equals 8 and e equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 8 nodes and 14 edges. Yeah? First question, what is the maximum number of relationships in this network? The maximum number of relationships in a network. How many interactions can we paint? What is the maximum? Hello? Throw away your phone. So, what is the maximum number of interactions in a network? It's not 14 times 8. So the maximum number of edges is n times n minus 1. Why? Because we have n nodes, and each node can, as a maximum, be connected to n minus 1. So n times n minus 1. This is the maximum number of nodes, of connections, sorry. So the first concept that we're going to talk about is the average path length, which is defined, please pay attention for a minute, is defined as the average number of steps that I need to go from one node to another one in the network. I repeat, average path length, the average number of steps that I need to go from one node to another node in the network. Mathematically, it's expressed like this: APL is the sum or a double summatorium of all the vertices or of all the edges divided by the maximum number of connections in the network. So this is the math, okay? Let's make an example. What is the APL of node number 1? Please pay attention, stop writing, pay attention. The APL of node number 1. Good. N and n minus 1 is known. So I just do this 8 times 7. And then how many steps I need to go from number 1 to number 1? 0. I don't need any step. I'm already home. How many steps do I need to go from number 1 to number 2? 1. 1 step. So 1. How many steps do I need to go from number 1 to number 3? 1, 2. Right? Plus. From number 1 to number 4? 1. Plus. From number 1 to number 5? 1. From number 1 to number 6? 1, 2. Number 1 to number 7? 1, 2. And number 1 to number 8? 2. So I get 3, 4, 5, 7, 9, 11 divided by 56. Okay. If I repeat this for APL for 2, for 3, 4, 5, 6, 7, and 8, and I add it up, I get the average path length of all the network. Please do it. The second concept is the clustering coefficient. Okay. The clustering coefficient is a measure of how groups are created within the network, of how triangles can be found in the network. And the formula is CC equal 1 divided by n times the sum for all nodes of 2 times L sub E divided by K sub E minus 1. In this formula, L sub E is the number of relations between the neighbors of E, and K sub E is the number of neighbors of E. Okay? So I repeat, the clustering coefficient is a measure of how groups are created within the network. The formula is 1 divided by n times the sum of 2 times L sub E divided by K sub E times K sub E minus 1, whereas L sub E is a number of relations between the neighbors of E, and K sub E is the number of neighbors of E. Let's make an example. The clustering coefficient of node number 1. Well, 1 divided by n. No, sorry. Clustering coefficient of number 1 is this. This will be, if we look at number, please look here. If we look at number 1, which are the neighbors? Well, neighbors are number 2, number 5, number 4, right? 2, 5, and 4 are connected to 1. So how many relationships do we find between these neighbors? 1 between 2 and 4, and 2 between 2 and 5. Between 4 and 5, there is no relationship, so L sub B is 2. 2 times 2 divided by K sub 1. K sub 1 is the number of neighbors of 1. 1, 2, and 3 times 3 minus 1. This means we have here 0.66. Any questions? Please repeat the calculation for all nodes. Continue now with the third concept, third and last concept of today is the degree distribution. Degree distribution. This is basically a graphical representation of the different degrees of the nodes in the network. The degree is also the number of neighbors. So I didn't say it before, but K sub E is the degree of the node E, okay? So when we say, okay, let's describe the degree distribution of a network, then we ask how many nodes have one node, one neighbor? How many nodes have a degree of 1? 0, okay? So no nodes have a degree of 1, 0. How many nodes have a degree of 2? How many nodes have 2 neighbors? This no, this doesn't, 3 doesn't, 4 doesn't, 5. No node has only 2 neighbors. How many nodes have 3 neighbors? Well, number 1 has 3 neighbors. Number 2 has more. Number 3 has 3 neighbors. Number 4 has 3 neighbors. Number 5, no. Number 6 has 3 neighbors. Number 7 has 3 neighbors. Number 8 has 3 networks. So 6 nodes have 3 neighbors. So we have here 6 divided by 8 of the network has 3 neighbors. So and 4 neighbors and so on and so forth. So 4 neighbors, it's going to be 3, 5, 5. So no node is going to have 4 neighbors, and 5 neighbors is going to be 2. So 2 divided by 8. So as you see, these numbers add up to 1. Okay. 6 divided by 8, 2 divided by 8. If they don't add up to 1, then something went wrong counting. Okay. So, and this is the degree distribution of the network. And with these 3 numbers, we can know a lot already of one network. Any questions? APL, APL, clustering coefficient, and DD. With these three KPIs or three numbers, we can describe a network in a very good way. Please put your telephone away. Thank you. So we want, what do we want? What is our goal? We want our logistics system to have a high or a low APL. We want it to be as low as possible. Why? Why? Because we want to bring material or information from A to B in our network as soon as possible. Imagine you have a logistic network of DM or Reve or something like that, okay? And you want to bring food from A to B as soon as possible so that it doesn't rotten, so that it doesn't get spoiled. So you want your average path length in logistics and in any system, you want average path length to go down, 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 down. Okay, the minimum possible is logarithms of n. You cool? This is the minimum average path length of a network in physics. Okay, a physical network. Our brain is a network of neurons, and the brain has this average path length. We will see later on why this is good. The clustering coefficient, what do we want with the clustering coefficient?
Also low.
Also low, no, wrong. Why is it wrong? We want our people in the network that work together. Yeah.
The lower the clustering coefficients, the higher is the HDL.
No, also wrong. So if I ask this question in the exam and you say it correctly but give the wrong explanation, then 0 points. Okay? So it's like a handshake. Thank you for participating, but 0 points. No, we want a high clustering coefficient because in our network, those guys that are working together, we want them to exchange. If you have a network, let's say you have this network. Okay, they are very highly clustered together. And then you have another network here. Everybody with everybody, okay? And then you have only one relationship here. Your APL is still high because all the paths from one of these clusters to the other cluster go through this. Okay, still high, but your clustering coefficient is high. Okay. Only if you have also these kind of relationships, your APL will go down. So it doesn't, there are two KPIs, not one. They don't have to do with each other. Of course, they describe the same network, and that means they are related somehow, but there is not a correlation, as you say. It's wrong. Okay? The reason why we want a high clustering coefficient is because we want highly clustered groups. People that work together should be very highly clustered together. This is the reason why we find, for instance, in organizations, we have different departments. Department of logistics, department of production, department of people that specialize doing logistics, doing production or doing controlling or something like that, okay? So we want a very high clustering coefficient so that we find specialization and efficiency. Okay? Any question? So if we combine these two, low average path length and high clustering coefficient, then we get something called small world network. Kleine Welt Netzwerk. Small world network. Kleine Welt Netzwerk. Okay? And this has certain property. These networks have an average path length of around logarithms of n. If we continue decreasing the average path length and continue increasing the clustering coefficient, then we get scale-free networks. And then what we get is an average path length of logarithms of n. The degree distribution of a small world network has following shape. The degree distribution of a scale-free network has following shape. Whereas this is K. What we find here in this area, these are called hubs. Please pay attention. These are nodes in the network that have a lot of neighbors, a very high degree. These are called hubs. And this is going to be a very important concept in logistics. Like when you fly, you fly through a hub in Frankfurt, or you fly to a hub in München to go to Dubai or to go to San Francisco. You don't fly from Nuremberg to Dallas. You fly Nuremberg, Frankfurt, I don't know, San Francisco, and San Francisco, Dallas. You fly from hub to hub. These are the hubs. You describe them by the degree. There are no hubs are nodes with a very high degree. Okay? Any questions? So we can take this number, APL, divided by clustering coefficient, and say this is a measure of so-called small worldness. There are other measures, but this is one measure. Okay? If somebody is interested, the the real measure used is the APL of the network minus the APL of a so-called Erdos-Renyi network divided by the clustering coefficient of the Erdos-Renyi network minus the clustering coefficient of the network. This is called small worldness parameter. This is not relevant for the exam. Only if you're interested, I just say it, okay? Erdos-Renyi networks are a special type of networks that are random, but are created through a specific process, okay? You can Google it. Erdos-Renyi, some guy called, coming from Hungary that first studied this. Your colleague would know. Very famous, studying network theory. But you need to know that if you compare average path length and clustering coefficient, then you get a measure of small worldness. And of course, we want this number to go down. Okay? Any questions?